Alright guys, getting into chapter 5. I'm still working on some trig stuff. So today we're getting the first part of lesson 5.1. So starting out with a little intro on complementary angles. If you can remember back to your geometry days, complementary angles are ones that add to 90. So we're going to take a look at what's going on with 30 degrees and 60 degrees in our unit circle. So if we take a look at this guy, you can see right here at 30 degrees, if you look at the sine value at 30, as well as the cosine value at 60, obviously those guys are equal. We could flip that around. We could say, take a look at the cosine at 30 and the sine of 60, and we're noticing that those are equal. So in short, we're basically seeing that complementary angles equal the other trig function. So when we say if our cosine of 30 degrees is rad 3 over 2, well, if you subtract this from 90, you get the sine function of rad 3 over 2. So we're seeing those guys. This works the same way with, say, a tangent or a cotangent. Those guys are complementary angles as well. So take a look at pi over 3, and if I said, what is the tangent of that angle? So if I did this divided by this to get my tangent, I would end up with rad 3. Well, if you look at his complement, if I did the same thing with the cotangent function, if I did my x divided by y, I would also get rad 3. So we're seeing that tangent and cotangent are also complementary angles to each other. So take a look at page 399 in your book here. There is a chart that lays those complementary angles out for you. And it really just says what I was just saying. So if I look at my sine and cosine, so if I have the sine of, remember this is like 90 degrees. So if I have the sine of an angle, if I subtract it from pi over 2 or from 90 degrees, I would get the cosine angle, right? And vice versa. If I were to do it this way and we took a look at tangent and cotangent, the same would also be true for their inverse functions. Right? So if I took the inverse functions of these guys, then I'm getting the bottom row. So again, just recognize on these that they are complementary angles. So in short, if we say something like the cosine of 30 degrees is something, then we know the sine at 60 degrees would be the same value. So let's go back to our notes here. Odd versus even functions. We're going to flip the page on in a second. We'll take a look at page 400. But an odd function, we dealt with this earlier in the year, so this is really just a reminder of the rules. An odd function is where I can replace x with negative x, and it changes the sign of every term in the function. Even functions are where you replace x with negative x, and there's no sign change at all. All right, those are our odd and even functions. So, is sine odd or even? So if I'd said, what is the sine of negative 30 degrees? Does that equal the same thing as the negative sine of 30 degrees? Right? So right here I have just plain old 30 degrees. So if we took a look at sine 30, we go back to our unit circle here. All right, so here's our sine value at 30 degrees. Nice and easy, 1/2. So if I replace x with negative x, in other words, if I did the sine of negative 30, what would I get? I would get negative 1/2, right? And you notice it is a sign change of what 30 degree was. So when I replace 30 with negative 30, my result does change signs to a negative, right? So that's how we know sine is an odd function. And so we could test that with any of these functions to see. But let me throw the rules at you. So we're going to look at page 400. And so here's the rule for odd and even functions. So again, sine of negative x does equal the negative sine of x, as we just saw. So I wanted you to see how that worked from the unit circle. Guys, the one thing you can do is, if you didn't remember the rule for this, you can always trace it back to the unit circle and test it the way that I just did with a real value. Like I plugged in 30 degrees and I tested the rule and showed that the result did change signs. Therefore, I know it's an odd function. The even ones, again, are the ones where if I replace x with negative x, there's no change. So if you look at the cosine value, right, on this one, if I replace x with negative x, my answer is still positive. And so I know cosine values are an even function. So here's how that works with a cosine value. So if I said, what's the cosine of 30 degrees? It would be positive rad 3 over 2. Well, if I replace 30 with negative 30, so what's the cosine of negative 30 degrees? It is still positive rad 3 over 2. So you can see there was no sign change, and that's why it's an even function. So, but there's all the rules laid out for you. It's the top of page 400. So that's kind of your reference when you need to take a look at those. We want to take a quick look here at example 2. So what I wanted you to see in example 2 is here's kind of one way that we could put some of these rules to use. So if I know that the cosine of theta is 0.34, and I'm being asked to find the sine of theta minus pi over 2, well, the first thing I would notice on this is the way that the cofunction identities were written, it was pi over 2 minus theta, not the other way around like this one's written. So one of the things that we can do, and this is an old Algebra 2 trick that you guys would have learned a while ago, is I can flip the order of this if I factor out the negative, right? And so what you're seeing in this first line is, here was the way that it was written. If I factor out a negative, that allows me to flip the order of what's in the parentheses, and now it fits the identity that we saw. We know that the sine of pi over 2 minus theta is the cosine of theta. That's its complement or its cofunction identity. Same thing. The negative is still there, so in other words, they're saying this is equal to the opposite of the cosine of theta. Since the cosine of theta was 0.34, the opposite of that would be negative 0.34. And so we're just putting together a couple of these identities to simplify and work it through. So there was just one I wanted you to see. Let me take you back to the notes. So now we're going to get into some Pythagorean theorem identities. And you possibly saw some of these in Algebra 2 last year in honors, potentially, if you guys got this far and did some of these Pythag identities. So let me give you some of the basics on this. So these are like the three main ones that we're looking at here. If I have cosine squared plus sine squared equals 1, this is the main one from where the other ones originate. But if you look at this one, I'll show it to you real quick on the unit circle. So if I'm looking at this, if I took my sine value squared plus my cosine value squared, my result is going to equal 1 squared. So on any of these guys, you could test that all the way around, but that's going to work in every case. Remember, in the unit circle, the idea is that the radius from there to there is 1. So my cosine value is how far I went to the right. My sine value is how far I went up, and that's what forms that right triangle. So it's like doing a squared plus b squared equals c squared. And in these cases and in the unit circle, since our radius is 1, that means the hypotenuse of that triangle is 1. Right? And that would work for any of these cases. So you could test that all the way around, but that identity is going to hold true for us. Let me show you two more. One of my goals in this is we can end up with quite a few identities. And so one of the things I try to show you is instead of memorizing all of them, oftentimes you can derive a formula from another formula. So for example, if I took this identity right here, and if I divided all three terms by cosine squared, it produces another identity. So I'm going to divide all these guys by cosine squared. So I'm just taking the original formula, I'm dividing all of my terms by cosine squared, and let's see what we get. So this divided by itself is obviously 1. Sine over cosine is tangent. And the inverse of our cosine function is our secant function. Just like that, we have another identity. So one of the other identities they want you to know is 1 plus tangent squared equals secant squared. So you can memorize that, but what I'm trying to show you here is you don't have to. If you just know how to get it from this one by taking this process, then it saves you that's one less identity that you're going to have to memorize. So let's do the same thing. If I were to go back to the original and divide all three terms by sine squared, so I'm just going to simplify each one. We know cosine over sine is cotangent. Sine divided by itself is 1, and 1 over sine, or the inverse of sine, is our cosecant squared. And we have our third Pythag identity. So here's the third one, and again, I could memorize it, or I can simply know how to derive it from the original formula, and then I don't have to memorize it. So anyway, these are the three main Pythag identities that we need to know. Guys, of course, any of these can be reworked, right? So for example, on this one, I could subtract over my sine, and I could say that cosine squared is equal to 1 minus sine squared, right? We could do that with any of these. So keep that in mind. We can always sort of rework these to isolate any of those given terms if we need to. So in this one, they're asking us to find sine find sine and cosine if the tangent of the angle is 3 and the cosine is negative, right? So in other words, I know that my tangent's positive and I know that my cosine is negative. So in which quadrant would we find a positive tangent and a negative cosine? Something we worked on last chapter. So down here in this one, you can see that our tangents are positive. If I take any y and divide it by x, I get a positive, so my tangents are positive. And because we're going to the left, I know that my cosine is negative. So in quadrant 3 would fit that description. So here's how we solved this type of problem in our last chapter. We would say, okay, well, let's draw a triangle. And this still works. We're just going to learn an alternate method here. So I know I'm in quadrant 3, as we just talked about, since my tangent ratio is 3 over 1. So from my reference angle, I'm going to do opposite over adjacent. And so there's my triangle, and if I use the little Pythagorean theorem, we figure out that our hypotenuse is rad 10. And now we could say, okay, based on those numbers, what is the sine value or what is the cosine value? So I could say, well, I know the sine value is opposite over hypotenuse, and I can get my sine value that way. My cosine value is adjacent over hypotenuse, and I can get my cosine value that way. And so that was the technique that we learned last chapter, and of course that still works. But what we're going to see here is I can use any of my Pythag identities instead of having to draw this right triangle, right? So I could say, here's one of those identities that we just came up with. I know that secant squared equals 1 plus tangent squared. That was the one that we came up with right here. And so if I just put in my value for tangent, since they said it was 3, then here's my setup for that. Right? And as we solve for secant, as I isolate the secant value in that, I'm going to get, it's either positive or negative rad 10. We know moving forward that which sign we would choose is determined by which quadrant we are in. So this still helps us determine the value or the sign of our result. Once we know our secant value, of course, I could just flip this upside down to get cosine. Right? So 1 over rad 10, which is what we got right here, is our cosine value. If we wanted to use these guys to find our sine value, now I could go back to one of my other functions, since, and you could use a few different things on this one. I could either take my cosine answer and plug it in here in order to solve for sine, but there are other options. Like, for example, we know that tangent is sine over cosine. And since they told us tangent was 3, I can use this little formula and just take my cosine answer, plug it in right here, and as I multiply it over to the other side, I get my answer for sine, which we discovered right here as well. Right? So there's going to be many techniques that we can use. So just drawing the right triangle was sort of the first technique that we used. Using these identities as formulas is just another approach to it. Let's try one. So on this one right here, for example 1, just modeled after the one that we just did, we're going to give this one a try. So we're going to do number 6. So again, they're going to tell us that our tangent is positive 5, our sine is positive. So in which quadrant are we working in? That's one of the first things I always try to recognize to make sure I get my signs right. So if my tangent is positive and my sine is positive, that could only happen in quadrant 1. So I know this is a quadrant 1 value, so automatically all of my answers are positive. Right? And so that's something I should recognize right off the bat just to make sure I get my signs right. So we've already done the triangle technique. So you could still do that if that works for you, but let me work with the new formulas for today. So again, since my tangent is 5, I'm going to plug into the middle identity that said 1 plus tangent squared equals my secant squared. So it looks like this. So this is obviously 1 plus 25, so 26. If I square root both sides, then we're seeing that rad 26 is our secant value. And from that, we can get any other trig value based on that. So again, if I know that and I don't need to put plus or minus because as we already mentioned, we already determined that our signs are going to be positive on this, right? All of our values, because we're in quadrant 1. So in order to move on from here, so if my secant's this, I know my cosine is the inverse of that. So cosine is now 1 over rad 26. And I typically still try to not leave my radicals on bottom. I would take the next step of rationalizing that denominator, and I tend to write my cosine value this way. So there's our cosine value. Now I can use those guys to get my sine value, and I have multiple formulas I could now plug these into in order to get my sine value. But on this one, I'm just going to use the formula they use. We know that tangent is equal to sine over cosine. Would look like this. And so if I simply multiply, so remember, dividing by a fraction is the same thing as multiplying by the reciprocal. Okay, so in other words, just be careful with your operations here. Sine divided by this fraction is the same thing as flipping it and turning it into multiplication. So it looks like this. Right, that would be the same thing. So instead of dividing by a fraction, we're always taught instead to multiply by the reciprocal. So this is really what it looks like, and now I can clearly see I just need to divide this over in order to get my sine value. So 5 over rad 26 would be my sine value. All right, let's jump down here to this guy. So simplify. So on these cases, we're going back to some basic factoring techniques. So if you look at this expression, we have cosine to the third of x plus cosine sine squared x. Guys, just a reminder, when they put the exponent on the interior like this, it is no different than putting it on the exterior like this. Right? It's the exact same meaning. We just tend to not write it this way. Right? We tend to write it this way, but those are the exact same thing. So it's still saying I am cubing that entire function. Anyway, so if we go back to this, so just some basic factoring on this. Keep in mind that when we factor, we are looking to create an identity. Right? So I want to factor it in such a way that I am producing an identity that allows me to simplify it. So on this one, there's really only one option. We would take out cosine of x as the greatest common factor. So that's what you're seeing right here. So if we took out the cosine of x, this is what would be remaining. And now we have one of our identities. We know sine squared plus cosine squared is 1. So we can simplify all that down to just be cosine of x. And so that's a lot of what we'll be seeing on these, is just using these techniques to just simplify what you have. We're going to try one of those. I'll try a couple of these guys. I'm trying to give you a few different looks so that you can see what's going on here. So on the first one, this guy's going to be very similar to the one that we just did. We're going to take out the greatest common factor, which would be cosine squared of x. So it's going to look like that. And as we just saw on a previous page, we know the identity that 1 plus tangent squared is equal to secant squared. I'm going to run out of a little bit of room on here, but that's okay. I'll just move that one over. So let's keep simplifying this. Again, we know secant squared is the same thing as 1 over cosine squared. So let me progress to the right here. So again, I'm replacing my secant squared with 1 over cosine squared. And obviously at this point, these guys would cancel out, and I'm left with just 1. So that would be the result of all this, would just be 1. So make sure that we do simplify those as far as we can take them. On this one over here, so we have sine squared over secant plus sine squared cosine. So again, remember that secant is the same thing as 1 over cosine. Because it's on bottom, if I flip that, it's going to move it to the top and become cosine. So now I'm looking at sine squared x cosine x, again, plus sine squared x cosine x. And so now from here, one thing that we can do is, obviously, since I'm adding this to itself, I now have 2 of those. So I can write 2 sine squared x cosine x. From here, you might look at this and say, well, why not then replace sine squared x with 1 minus cosine squared of x? But as we start doing that, you would see it's definitely not simpler than what we have now. So we do want to keep things as simple as we can. Let me give you a couple bonus questions here on the last page, and then we'll call it quits. All right, so sine squared. Again, guys, in some of these, it really can be tough because you might have multiple options on where to go. So with this one, a couple things that we can do. So sometimes you just sort of have to play with these a little bit until you find a path that is allowing you to put some identities in and allowing you to simplify. If you look on top, we have conjugates, right? I have secant plus 1 times secant minus 1. So think way back to your basic factoring that you guys have done for years now. So if I did a plus b times a minus b, right? If you were to FOIL that or distribute, you're going to end up with a squared minus b squared. All right, so just one of our old multiplying and factoring techniques that we've looked at, like a difference of squares, comes out to be this. So anyway, that's what we have going on with these guys. We have conjugates. So I know I'm going to get this result, which is just secant squared minus 1. As I look at the bottom of this, I do know that sine squared is 1 minus cosine squared, but we have to be careful. I do want to make sure that I'm left with things that will simplify. So even though I could replace this with 1 minus cosine squared, I don't know that that would help me in this case. So what we're going to do instead is I'm going to keep my sine squared as it is for now. In fact, so let's leave that. So here's what I'm seeing on this. If I have secant squared x minus 1, as we saw in our middle identity, the second one that we did, secant squared minus 1 is going to equal tangent squared. So I'm looking at tangent squared of x over sine squared x. And so now we got to go back to something we learned in prior chapter, which is we know that tangent is sine over cosine. I'm going to separate these just so you can see my next move a little more clearly. So I'm going to keep it as, I got my tangent squared of x times 1 over sine squared x. All right, that's really what this means right here. So I'm just separating them so that you can see what's going on in my next move. So we know that tangent is sine over cosine. So here's what I have now, and now we can see the obvious cancellation. Those guys can go. I'm left with 1 over cosine squared, which we could write that as our answer, 1 over cosine squared. But typically, since it's on bottom, we would probably see it written instead of 1 over cosine squared, we would see it as secant squared of x. And we're going to try one more of these. So one of the big issues we're seeing on this is I have two separate fractions. These are not being multiplied, so I can't really combine them very easy. So what we're going to need to do on this is create some common denominators. In other words, this whole thing is going to have to be one big denominator. So I'm going to have to multiply my cosine of x to this side and 1 minus sine of x to this side in order to create common denominators. So I'm multiplying my cosine over here. So it becomes cosine squared of x. I'm multiplying this over to here, and I'll just write that out so we can see it. So now I've created one big common denominator of cosine x times, I'll write it this way, 1 minus sine x. So that puts me here. So now I only have one fraction instead of two, right? And so now this helps me simplify what we have. If I distribute my negative sine x in my numerator, it's going to look like this. And hopefully you're already seeing what's going on up top. We're going to be allowed to do. So here's where I'm at now. So now what we're going to notice is just those two terms right there. I have a cosine squared plus a sine squared. So if I just isolate those two terms, I can replace those with a 1. Right? That was our first Pythag identity. So that leaves me with 1 minus sine x. Puts us right here. Now you can see the cancellation. 1 minus sine x can cancel out. I'm left with 1 over cosine, which would probably be more appropriately written as secant. So I'm just trying to give you many different looks because obviously there's a lot of techniques and approaches here. So hopefully that helped with seeing multiple examples. But that's it for part 1.